So, welcome to the second lecture of application-specific signal processors. Uh, in this lecture, we will first revisit the material that we presented in the previous lecture and then go through a more detailed example. This will help you with doing your project work later at the end of the course. So we saw that fixed point had multiple advantages that we're simplifying the design in terms of hardware resources and power resources, and helps to add performance because it entirely is based on regular integer operation. But the programmer should take care of numerical errors that may arise due to fixed point operations, of which are overflow and underflow. So uh, a fixed point format is made of this manner that uh, we have an integer variable. We dedicate, this is virtual. The compiler is not aware of this. We dedicate some LSPs to the fractional part. Then we have our point, which segregates the integral part and fractional part. It's like you have 1.3. This is the same thing, but in binary. Then we have the integral part, which basically is the integral number that we have in our fractional arithmetic, and one bit for the sign bit. So in this example, we have a 16-bit integer. 6 bits are dedicated to fractional part and 9 bits to the integral part, and 1 bit to the sign. If the fractional part is larger, that means we will have high precision, and so to speak, we will have less risk of underflow or rounding. But on the other hand, because we now have smaller number of bits dedicated to integral part, we will have a smaller dynamic range. An extreme example would be that we stretch all fractional parts up to bit number 14, starting from bit 0, starting from this bit 1. So we take it up to this 14th bit, and then we just dedicate 1 bit to the integral part. So then it means that the maximum number that we can represent is 1.99 something, and the minimum number that we can represent is when this sign bit is negative, is indicating that the number is negative. It will be minus 1.999, and so on. And if we, in the other side of the spectrum, if we dedicate all of these bits except this first bit to integral part, then this fixed point will be located here. So we will be able to represent very large numbers and very small numbers, but our precision will be limited to only one fractional bit. And one fractional bit is equivalent to the power of -2. By the way, it's useful this to be explained here. If you remember, when we were converting numbers from binary to decimal, we would assign some weight to each bit. So first bit, for now, ignore the fractional part. The first bit will be 2 to the power of 0. The second will be 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. So if we have 1, 0, 1, 1, we will multiply this number in its associated weight. So here we will have 1 multiply, if we have 1, the weight that we always have for this first bit is 2 to the power of 0. So that will be multiplied. The same, the weight of this second will be 2 to the power of 1. The same of this will be 2 to the power of 2, and so on. In fractional part, we go in opposite direction. So we will have 2 to the power of minus 1 for this one, 2 to the power of minus 2, 2 to the power of minus 3, 2 to the power of minus 4, and so on. So if we have only one bit as fractional part, we only can represent numbers like 2.25, 2.0, things like that. We are not able to represent we wouldn't have more precision in our in fractional number. Now we have to scale. We had, if you remember, we had to scale numbers before we use them in our program. So assume that we have some number that is this should have been a float. Assume we have had numbers that we know the size of the dynamic range of the number. We are sure that the number wouldn't be less than minus 1.5 and more than more than 5. So this will be the dynamic range for our numbers. Then to be able to use them, let's say in 16-bit integer format as fixed point number, we define new variables and we scale that number with some factor. So, and this factor is decided by this maximum error that we can tolerate. So we multiply it by that factor, and then let's say we go here and we look at our operation and we analyze analyze the situation given that we have these conditions, meaning that we know what is the dynamic range and we know that what is the maximum error bound. So, and we see if our scaling factor meets our demands or not, and then we adjust our scaling factor so that we wouldn't have overflow in these operations, meaning that the result would not be larger than 16 bit, or wouldn't be higher than, it wouldn't be larger than what we have in our dynamic range, and then no underflow, meaning that we will have errors that will be larger than this. So in this example, we chose first that the scaling factor will be 8. So if we have a scaling factor 8, it means all the numbers, all the bits here should shift to left by 3 bits. Because we are multiplying in 8. And then we will have 3 empty bits here dedicated for fractions. So first, before we implement this, we multiply we determine our scaling factor, and then we multiply our numbers in that scaling factor, and we save it here for using in the fixed point format. And if it's not enough, then we add to our scaling factor. In another example, we assumed 12 bits for our scaling factor, for our fractional part. So our scaling factor will be 2 to the power of 12. Why? Because we are shifting 12 times to the left and right. And notice something. In reality, we don't implement it by multiplication. We implement by shifting operation. Uh, so as I mentioned, you can face overflow in such operations. So when you are doing fixed point, again you have to analyze it as a programmer. But most of the time, when you are doing fixed point operation, you have to scale down after operations such as multiplication, because here you have a fixed number, that a fixed point number that's multiplied in another fixed point number. In this case, of course, you have a constant that is multiplied in fixed point number. But if you are multiplying two fixed point numbers, Remember, the scaling factor will be applied twice. So you have to bring it back to the situation that we have one scaling factor applied one time. And when we finish all operations, again we get rid of that one scaling factor as well. Also, when we have these middle operations, that for example we add this to this, there can be scaling, there can be overflow. So we have to implement some necessary shifting operations here to make sure that overflow doesn't happen. Uh, so the last question in lab one was that what is the difference between these different implementations of the filter. So the filter code was the same. We just changed the numbering format. So if you had zoomed in and you plot the filter response, you would see that the uh, ideal, the one that implemented using 32-bit floating point, that is very close and that's actually very high precision. That attenuates the signal is on the right frequency being, but the ones that are implemented with lower precision numbering format, they don't show very precise attenuation. So they attenuate the signal that resides on beam 994 hertz beam. If I remember correctly, 32-bit floating point and 32-bit fixed point integer with the scaling factor that was chosen in the lab, they performed fine, and the worst results was from 16-point floating, 16-bit floating point. So now that we have covered the first lecture, let's discuss the topic of the second lecture. So the programmer processor can have different architectures and different flavors of architectures. We will see here what processors are used in general purpose applications and what kind of process architecture we will use. But first, we look into general purpose architectures, and we will see why we move toward some other architectures, and we are not using the regular processor. So, as hardware designer, we design a processor, and we provide an instruction set, a set of small instructions that the software can be based on. So the programmer writes the code, let's say in C, Java, whatever. That code, through compiler or some translator, is translated to the instruction set of this specific processor. So if you have if you write a code for desktop computer, the compiler for the desktop computer generates appropriate machine code that matches the instruction set of the desktop computer. If you take the same code and you implement it for mobile processor, and it's, let's say, your mobile processor, and it's, let's say, the former was Intel in the desktop, and in your mobile you have an ARM processor, and that has totally different instruction set. Then again, the specific compiler converts your code to that instruction set. So we from the from the language, the software, we get the machine code, and the machine code given to the processor, and processor does the operations one by one for us, and then results in output. Now we can't have programmers to write directly in the in the machine code, or knowing instruction set of each processor. That will be a very difficult task. So we have compilers that compile human readable code like C, C++ into the machine code, and that compiler generated machine code will be fed into the processor. So instruction set of a processor looks like something like this list. That this is for Intel processor. So it it gives you some instructions that these are not actually in this manner, that these are text, these are binary code. So when you insert this binary code in the in the processor's ILU, let's say arithmetic addition hardware gets activated. When you insert the second code, which is AND code, then logical AND hardware will be activated. So it's like a multiplexer inside the processor. You insert these codes, and some specific hardware gets enabled. Uh, so there are different types of there are different categories of processors that each category divides the architectures in based on some criteria. So if we divide architecture based on the instruction set, meaning what kind of instruction set we have in the processor, we have two types: CISC, complex instruction set computer, and RISC, reduced instruction set computer. So complex instruction set CISC processors have lots of instructions. So for most of the things that we may need computer to provide computing, they have some specific hardware. An extreme example would be a processor that doesn't implement, let's say, log or sine functions as software algorithm, but they have a specific hardware for that. And there is a and let's say log or sine are part of the instruction set, and also the instructions are very complex in a manner that for example, these add instructions can have three, four types of flavors. So this makes the instructions set very, very big and large, and the hardware complex. But the idea was that if we implement everything in hardware, and since hardware is way more faster than software, we will get higher performance. But then that idea later was challenged by risk idea that they understood that if you have some optimal number of instructions that can support any kind of software, you end up doing better actually in terms of performance and power, because most of these hardware that that are supposedly there to accelerate the software, they are rarely used. Instead of having one log function instruction, I can have 10 add instructions. So because add instructions is obviously going to be used more often than some log or sine or other mathematical function. So that hardware can be dedicated to more useful operations. The other categorization is based on the structure. So we can have pipeline structure, we can have VLIW, we can have VLIW that's pipeline, and in this course we will use some processor structure called TTA, transport triggered architecture. So on top of these, we can have SIMD instruction support for these kind of processors. This SIMD, you can think of them as some sort of accelerator. You know, when you are doing when you do gaming, you add a GPU as the accelerator to the or co-processor to the main processor. So here is the same thing in this embedded setting, that we can have some SIMD processor as some sort of a co-processor that takes care of heavy processing stuff. So a basic blocks of a processor are these, that we have an instruction fetch unit that is responsible to go to the memory, get the next instruction that needs to be executed. You know, the programmer writes in a code. That code is compiled to a list of machine code, and that will be loaded into the computer's memory when we want to execute that code. Instruction fetch unit based on the current instruction counter and branches, jumps, etc., etc. Decide knows what next instruction should be fetched. So this is responsible to talk to instruction memory, for example. Then we have instruction decode unit, that, you know, these instructions are a large number of bits. Some part of that bits, let's say first 5 bits, first six bits, they decide what operation gonna be activated. Is it an add operation? Is it a logical AND operation? So that needs to be decoded, and at the same time, we need to know that if the operands, you know, if we decide that that's an add operation, there should be some two numbers that we add to each other and one destination. So where that source resides in the memory, in the cache, in registers, or is it an immediate value, and where I have to write to. So these things are decided here in instruction decode. Then we have functional units that they do the actual job. So this decoder activates the add unit, activates where the data should come as operand and where it should go. It You can imagine it routes those or opens those ports in the functional unit, and then the functional unit does the operation and just puts the data where the decoded unit had decided it should go. And then register files keep the output from the functional units, and then if necessary we write it to memory. So we will have such an a structure as a basic processor. So we have some instruction memory, then we have instruction fetch unit, then we have instruction decode functional units. They write to the RF, and if needed, read from RF. RFs are register files. These are some sort of very fast memories that are close to the functional units within the processor. So, and then after that, we write it to the data memory, or if it's needed, to some input output port. So, this exercise we were supposed to do it in the class, but I will assign it as a separate exercise in the Moodle. So method to increase the performance is pipelining. So what we do, we had these stages. We put intermediate hardware here that kind of separates these stages from each other, and then It enables us to have them operate on different values at the same time. So if you imagine this case that you would like to have your clothes being washed, then being dried, and then being mangled, then you can do this, that you first put your first batch of clothes, or the first person puts his clothes or her clothes in the washing machine, then takes it and puts in the dryer, and then dries it, and then mangles it, and then exits the laundry room. And then the next person comes into laundry room and uses the washing machine, and then laundry, and then mangling, and so on and so forth. So when the first person is inside the laundry room, and for example is using washing machine, nobody is able to use the dryer and the mangler. And when the person is using the dryer, nobody is able to use washing machine. But this is very inefficient. What if we have these 3% these 3% in a line? The first person comes in, use the washing machine. Then, while the first person is moved to the dryer, the washing machine is freed. So the second person comes in and uses the washing machine. And then, while the first person is using the mangler, the second person is using the dryer, because the dryer is now freed, and the third person is using the washing machine, and so on and so forth. So this is called pipelining. As we increase the stage of the pipeline, we increase the amount of parallelism that can be achieved within that pipeline. So instead of having very long period clock, so very long period clock means a lower clock frequency. So instead of having, let's say, a CPU with 100 megahertz, I will have a CPU with 500, 400 megahertz, 4 times faster, and now I can do things multiple times faster. So basically, we break down a clock period to a smaller period, and then we make these stages independent of each other by putting some registers here, some flip flops. So if we have some instructions like this, that let's say this instruction says that load word, this instruction subtracts two things and puts it in this destination. This one adds, this again loads, and this adds this kind of thing. Instead of having to run this instruction through all of these and then going to the next, we can do pipelining. So when this instruction is being fetched from instruction memory, uh, 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 of course, the rest of the pipeline is empty. Then, once this instruction goes to the next stage in the second cycle, the first instruction can be fetched from instruction memory. And then, when the first instruction is in the third cycle, is in the ILU stage, the second instruction can go in, and so on and so forth. But pipelining is not perfect. The reason is that they don't let's say they don't make 100 stage or 1,000 stage pipeline. Is other than being wasteful after some point, this nature in the programs that we write. We can't run the pipeline perfectly. In this laundry example, nobody is dependent on the previous stage. So when the second guy wants to do the dryer, he doesn't care if who is the when the first guy wants to use the dryer, he doesn't care that who is the first one, and this doesn't affect how they will use the washing machine. But in the program code, we don't have this situation. Often we have this situation that the current instruction depends on the previous instructions. Or we don't know what we should do, which instruction we should execute next. We have to run all the code to some point until we decide. Or there are two instructions that both of them wants to use the same unit, the same hardware. In this laundry example, we assume that all of them finish in a certain period. I mean, each of these wash, dry, and mangle stages, they finish it in a same time frame. But in reality, washing takes 2 hours, drying takes half an hour, mangling, let's say, takes 20 minutes. So the times can have overlap. So it's not this perfect pipeline. So that will result in structural hazard. So as I mentioned, in data hazard, the situation is that for computing this current instruction, you need results from previous instructions that are unfortunately are still within the pipeline. They are not finished. They haven't got out of the pipeline yet. For example, you want to add a value to some other value. That other value is result of some operation in previous instructions, and those operations are still traveling through the pipeline, and the output is not ready. And this is data hazard. So this will force to stop the pipeline and lose the benefits, and the pipeline will go on empty. So what they call bubble will go here. So nothing will go to the next stage because this instruction cannot be executed. Then we have control hazard. These things like branches or jumps or for loops, because they have conditions inside, and those conditions usually are some mathematical operation. Something added to something else should be less than something. Then you jump or you continue the for loop, and that calculations needs to be carried out, and it it's usually the case that those computations they are in the pipeline while we want to decide that are we taking this if, or we are not taking and jumping to some other place. So that forces us to stall the pipeline. And the last one is the structural hazard, that this can be that in a situation that register files are full, or two consecutive instructions wants to use the same hardware. So in this case, this is a load, this is a sub, this is an add. So sub and add, both of them use the let's say adder unit, because this full adder can be turned into subtractor. So they use the same arithmetic unit. And let's say it really can't be finished in one clock cycle. So while the sub is in this ILU, add will arrive and ask to get into the ILU, but can't, because that part of the ILU that does addition operation is already occupied by sub. So here we will have a structural hazard, and the pipeline has to stop. So These these issues made especially complex instructions, these CISC type instructions, very complicated to implement in pipeline. So one of the benefits of RISC was that it simplified the pipeline, and simplified writing a compiler that transfers that code optimally to the instruction set. Uh, so there is a concept named dynamic scheduling. So if I have instructions in this manner, and I will have 1,000 instructions, and I know that my pipeline will be stalled, will be stopped because of these hazards, data hazard, control hazard, and structure hazard. Then I can have an extra hardware other than my actual. This is the actual processor. This is what this is who really does the job. But because we want the pipeline to run with full capacity all the time and with no stalls, we have to feed it all the time with instructions. But we can't because we have hazards. Then what we do, we add extra hardware that looks into the instructions that are coming and tries to schedule them, change their location in the line without hurting the programmer's logic. You can't randomly change the location of the instructions because then the instruction will be meaningless. But you can change it in a manner that you don't hurt the logic, so you identify the instructions that are, or instruction segments that are independent of each other, and then you move them around. And also you can check that if these consecutive instructions will have hazard or not. And all of those hardware, they add a lot of complexity. Of course, they add a lot to the performance, but they add a lot of complexity. So those are called those are doing dynamic scheduling to keep the pipeline busy. If we need more performance, we can have superscalar processor, meaning that, okay, instead of having one line of processor here, we can have two, three, or four lines of processor. It's like we, instead of having one dryer, one washer, one dryer, and one mangler, we have another set of washer, dryer, and mangler. So we can add performance, and this scheduler, dynamic scheduler, will have easier time finding resources. Uh, so if we look at a superscalar processor, by the way, your desktop processor is this kind of processor, meaning that it has a dynamic scheduler. Your mobile's main processor that runs operation system is this kind of processor. If we look at the hardware resource of this kind of processor, this is, I guess, an Intel processor. So all of these hardware in this orange block, all of them are doing this kind of dynamic scheduling. Complex decoder, complex fetch, scheduler, branch prediction. Then then we will have to have larger caches, let's say instruction cache, so that the scheduler is able to look through the instructions, to look through a huge number of instructions, to be able to find those segments that are independent. If you have a small window of instructions, it would be difficult to find independent segments. Then there is another interesting thing here, that you see this large area for floating point. If you use fixed point operation, that's gone. We get rid of that. So you see that a large area is dedicated for caching, instruction caching, scheduling, and that hardware can be used elsewhere. So if these hazards happen when the generated code has unpredictable behavior. What we discussed in the previous section, the previous lecture, that signal processing codes, as an example, they have this benefit that they have regular structure. They are predictable what they can be done, and then they are um, heavily utilizing some specific resources. So instead of having like a general purpose processor having support for any kind of operation, we can focus on only the operations that are on demand. And we can get rid, because of predictability, we can get rid of this dynamic scheduler. and probably half of this cache, and many other components here. And we can dedicate that to useful operations. And by the way, we can't do this for, let's say, an operation system or some other application programs, because they have this unpredictability nature. So we need dynamic scheduler for those. But for DSP ones, we don't. So static scheduling is like this, that we write a code, that code is compiled to machine code, then the compiler knows what is your architect, and then you as the programmer give hint to the compiler and say that, look, this will happen in this branch, that or this part, or this part is independent of this part, so you provide this kind of things. Or don't worry about this pointer, although this is somewhere in memory, but I guarantee it won't be changed, so if you fetched it one time, no need to refetch it again. So this sort of thing. Then we can, instead of relying on this dynamic scheduling, we can schedule the code in the compile time in a manner that minimum number of dependencies or hazards are within the code. So we will be able to run the code with minimal stall, without having to rely on these schedulers, dynamic schedulers. So, as I mentioned, DSP programs have a great deal of parallelism. They are pretty much predictable, so the compiler can statically schedule them, and we can avoid using expensive dynamic scheduling. And what happens if I save the cost to make these scheduler? Well, I can have. Do you see this small ILU here? I can have two other ILUs here, and this ILU is the one that does real computation. So I can have three times more real computations instead of having all of this hardware for scheduling. And who guarantees that this will be used and 100% used, or with a high percentage be used, and they wouldn't be sitting here idle? Compilers, a static scheduler will try to do that. So having said those, now we move to an interesting architecture that is a perfect fit for this situation that we discussed. So very long instruction word architecture. So you see here, I mentioned that we can have multiple ILUs, So that multiple ILUs can be implemented in this format of VLIW. So instead of instead of having a regular processor like this that has an ILU, some floating point unit, we can have the whole thing here like this as a lane, let's say. Within this lane, there is an ILU, there is an LSU, there is an FU. LSU is load store unit, FU floating point unit. So in a sense, we have multiple small processors put together next to each other. Here is a 3-lane VLIW processor, means that there are 3 small processors next to each other. And you can have instructions for this processor running in parallel to instruction to this processor, instruction to this processor. This is similar to that superscalar concept, but there is a trick here that distinguishes VLIW. VLIW relies on compilers static scheduling. So this is an example of VLIW code. This is not very good scheduled code, because you see we have 8 lanes. It's like we have 8 processors in parallel, and these lanes, all from lane 2 to lane 8, they are almost feel with almost all of the time they are filled with no operation. So nothing was assigned to them for them to do. So they are just sitting there idle, and only the lane one does it in this sequential manner, and this becomes very, very inefficient. So the compiler, the VLIW have many lanes. The compiler is responsible to fill those lanes with instructions. In Superscalar case, that was the dynamic scheduler who was doing that. But here we don't have dynamic scheduler, and we actually got rid of dynamic scheduler to be able to have multiple lanes. So the software and compiler take care of too. Notice VLIW can be pipeline because these are essentially these simple processors. So you can have it, let's say, 5 stage of ILU here, but that of course adds to complexity. Uh, and if we have a good static scheduler and some good code that can be statically scheduled, not all codes can benefit from static scheduling. Then we will have such a situation that, but still you see the lane 8 is always empty. But we will have such a situation that all lanes have something to do, and we have high utilization. Now, if we were supposed to run all of these instructions sequentially, we would have to run first this, then this, and then continued here, lane 2, lane 4. But now we run all of them in parallel. So if we have 1,000 line code, and let's say we have 4 lanes VLIW, ideally we can run that 1,000 lines of code instead of running in 1,000 cycles. We can run it in 250 cycles because we run it in eight in 4 lanes. The examples of VLIW in real world are numerous. Texas Instruments signal processors, digital signal processors are 8 lane VLIW. Qualcomm hexagon processors that almost all flagship mobile phones currently you have these hexagon DSP processors. If you look at the specifications of these Android mobile phones, you will see some Snapdragon processor or hexagon specifically there. Toshiba use that and many others. So the one problem with VLIW is this situation that imagine I have some data. Let's show it here in this real code. So imagine I have this instruction produces some data that must be used here in lane 6 by this instruction. You know, I have two options. Either I cancel them to be scheduled statically, and then I put it in the same lane. So this instruction will not be able to run in parallel or immediately in the next cycle here in this lane, or even in the lane 6 at all, because its output is in lane 1, and we have to wait. This instruction has to wait for lane 1 to pop out its output to the memory or cache. Then this guy goes to the cache and fetch the input and uses it here. Or we don't do scheduling at all, static scheduling at all. And our interest is to keep all the lanes busy. So what they do is a technique that's called forwarding. So they have an interconnect network between these lanes, between these lanes here. So this lane says, hey, lane 1, I need the data that you have it now. So this lane 1 will pass that to lane 3, and lane 3 will use that. And that's an interconnect network. It's okay if you have 1, 2, 3 lanes, but when you have 8 lanes or 16 lanes, that's actually where VLIW really shows its power. Then this interconnect networks becomes extremely complicated. For that reason, well, this is a depiction of that interconnect network. So there are register files of each lane, and then the functional units write to those register files, and then those write to the interconnect. Uh, we have this problem with VLIW, that this scalability, you can't use like more than 4-8 lanes. Other beyond that, it becomes unreasonably complex for the interconnect network. So this limits scalability. The code density, even in this good example that I wanted to show you, you see that you can identify lots of no operations, here and there, and this is bad. It means that this hardware are sitting there consuming power, doing nothing. So it means less efficiency. Customer is unhappy too. He paid a lot to the chip because that chip was a large chip. It consumed lots of hardware, but that doesn't deliver the performance. For that, we will use a different architect that we will see in the next lecture, and then that will be our architect of choice for designing our processor for this course. The last trick is similar to VLIW, but I felt that I have to mention and clarify the difference. So we can add SIMD instructions. In this, we can have oil use that do SIMD instruction. And what is this SIMD instruction? It is an instruction that it's not like VLIW. In this VLIW, you have parallel instructions running, but each instruction does something. This is call, this is NOP, this is autoput, this is NOP, this is, I don't know, MBK what. So each of them do something. We can have SIMD instructions that it's similar to VLIW. It's multiple, something like this, multiple lanes, but all of them do the same thing. The benefit is that this is very, very simple compared to VLIW. The advantage is that we have many, many situations that you have, let's say, 128 numbers need to be added to another 128 numbers, something called vector addition, vector operation. We can do it in this manner. Let's say we have a SIMD instructions that supports 4 integer values to be added at the same time. So the compiler support will, of course, have such a keyword, some variable keyword, that we have int 4. So it means that it's an integer, but it's actually 4 integers, connected to each other. And the ABC, and these are not 1 integers, they are 4 integers. So instead of having C1 equal A1 plus A2, B2, B1, C2 equal A2 plus B2, and so on, we will have ABC, C equal A plus B. And all of these 4 addition operation will be done at the same time. The vector operations are not like 4, 8 or something. They are not like VLIW. They removed lots of complexity and they gain lots of simplicity, and the cost that with SIMD you lose flexibility, and but instead you have a huge performance if you can utilize it properly. So this was the lecture for the second session. There are 2 assignments that I will post on Moodle, and please try to do them. That will really clarify the things that we discussed today.